Hello everyone. In this particular lecture we are going to discuss how to assess the quality of a DM and especially quality of DMs which are freely available. As in previous lecture we have discussed that there are several freely available DMs are available on internet. The USGS DM, SRTM DM at different resolutions, even including at 1 kilometer resolution as well. And nowadays recently they have started giving also 30 meter resolution, and then earlier this 30 meter GDM, that is global digital elevation model for entire globe at 30 meter resolution is available. So depending on the process or the inputs of the data, the quality of DMs would be there. But why quality is so important? Because we are going to use this digital elevation model to drive various outputs, and if we know that the input itself is having errors or problems, then your outputs will get affected, their quality will get affected. So therefore it is very necessary to understand the limitations of each digital elevation models, the errors associated with different type of digital elevation models which we are going to use in our GIS analysis. So this is one part which is least discussed or least incorporated in literature as well, the quality and the error components, which we will be emphasizing in this particular error, because we must know the inherent errors which are present in DMs and other data sets which are going to inside your GIS database, which will be later used for different types of analysis. And because there are different DM derivatives, tens of derivatives can be derived from DM which are very sensitive to the quality of DM. For example, a slope map or a aspect map, gradient map, through surface hydrologic modeling one might be going for watershed boundary, maybe the stream network, stream ordering, and sediment power index. There are many outputs which can come directly from DMs, these derivatives. So if the quality of DM itself is poor, then definitely this will affect our output. And knowledge about as I have mentioned already, that the errors which are associated with different DMs, even your own interpolated DM, then this is really very much ignored, not much discussed, but we must understand the inherent errors in a DM, and wherever it is possible try to minimize those errors, because otherwise errors will propagate in GIS. Now, which are the errors in DM are likely to be larger, in which areas, especially in the shaded slopes or smooth and featureless terrain. Now, two extreme terrain conditions can bring errors. One is like hilly terrain like Himalaya, because SAR interferometry technique is looking in off nadir direction, and if there is a say valley, so it is only looking one side of the slope, not the other side of the slope, and therefore it will have problems in a hilly terrain. Whereas a raster DM which is using the stereo pairs, because in a hilly terrain lot of areas in a hilly terrain may go in the shadow, and then these shaded areas will have problems. So each type of digital elevation model, if we consider only say freely available digital elevation models, they are suffering for one type of problems or another. Similarly, if it is a smooth and featureless terrain like a desert area, then you do not have any much features or dunes very prominent one, and then it is very difficult to assess even the quality of DM, and therefore there is more likely to have more errors in a very smooth and featureless terrain like deserts or terrain like Himalaya. where so much ruggedness is there that different techniques are having different problems. The requirement of high resolution digital elevation models for these two extreme areas, especially of hilly terrain of Himalaya, is much more, because there are a lot of many things which are done in Himalayan terrain, and your topo sheets are having contour intervals which are quite large. So you cannot definitely you cannot rely all the time on the topo sheets, because if you put say in a 50,000 scale map, even 100-meter contour interval, these two contours are coming very close to each other. So you cannot go for even, then you go for a larger scale maps. That means you require more input, and hilly terrain like Himalaya, it becomes very difficult. But the requirements for a high resolution digital elevation model, and that too accurate digital elevation models, are much more difficult for Himalayan terrain, and different techniques are suffering. The digital elevation models which are derived from different techniques are suffering from one type of error or another. So this assessment must be there before we employ such DEMs, and DEMs errors are especially variable, because depending on the terrain they will vary, and also especially autocorrelated. That means the correlation among values is also there. So sometimes you get a very smooth surfaces, sometimes you want to represent a very rugged terrain, and then you are having problem. Another issue is about the uncertainty. As you know, the digital elevation model is a approximation of reality, and the DM is a model of the real world or features or phenomena, which is a terrain, and here the goal of spatial modeling is to produce close approximation of reality, because it is a representation. It is based on the Shannon theory that within that cell all elevations are having the one value. So this is basically a sort of sampling or assumption is there, and this whatever the goal, whatever the purpose, there may be there are lack of knowledge about how good a representation of reality is required, because we do not know for what, if we are very much sure that for what purpose we are going to use, then we must know the errors associated with our input data. So this whether our input data is really representing the reality in a accurate way or true manner, that has to be understood, and how well a model represents the reality, which particular digital elevation model derived from variety of sources will fit to our requirements, and how reliable the conclusions are which can be drawn from the model. So when you drive the outputs of different derivatives from a digital elevation, how much rely you can have with them. Like if you use a digital elevation model and drive a slope map, so how accurate, how reliable that slope map. Again, this reliability or this confidence will come once you are sure that your digital elevation model is really truly representing the real terrain conditions. Then only you can rely, otherwise you will have little less level of confidence. So this lack of knowledge, which we can represent or express as uncertainty with the digital elevation model. And this uncertainty has got two components. One is the uncertainty about the quality of data, and that uncertainty about the quality of processing applied to the data. So because if we talk say about the SAR interferometry based digital elevation model, which have been derived from this SRTM, then this is based on one particular remote sensing technique, which is radar remote sensing or active remote sensing. So there are issues and associated problems for different terrain with the radar data. So that will come under the uncertainty of quality of data. Then this data, when it was acquired by this mission, then this data has been processed, and then digital elevation models were created. So how accurate that process was, so that uncertainty will come in the quality of processing applied to the data, because each processing will might bring certain errors. So those errors should also be kept in mind, and basically those who produces all these digital elevation models, generally they declare that what kind of errors their data is suffering from, but they don't declare specifically for different terrains. So for if I am going to use for Indo-Gangetic plain, I may be sure that yes, whatever the data I am using is quite accurate. Say example related with SRTM. But when I go for a hilly terrain like Himalaya, then I know that because of radar techniques, this is having some limitations, some problems, and void issue which might be there. So depending on the terrain, our application or utilization of different DMs should be there, and this is our own assessment through experience and some analysis that strategic GDM is quite good for Himalayan conditions like Himalayan terrain or terrain which is highly rugged, whereas SRTM is quite good or quite accurate for the plain areas like Indo-Gangetic plain. So all DMs are not suitable for all kind of terrain conditions. So this thing has to be remembered. How we can assess this thing, that for that you need to have some independent collection of some say point data, and which you can use as a control points or control ground control points, and then compare what the value in a cell of a DM of different DMs is being carried. So whichever the DM which is having the close representation of your controlled or these ground control points, you can say that that DEM is representing truly my terrain and that particular terrain than a different DEM. And therefore the data quality is fundamentally dependent on the degree of errors within the data set. This is very important here about the data quality. Errors is a difference between a data set value and the true value, because when the data is being acquired through remote sensing techniques or some other techniques, we do not have all the time the true values, and since DM is a continuous surface, we do not have the true values to check continuously, corresponding continuous values, and therefore assessing the errors becomes very difficult. The true values we might be having only few point values, only against those point values we can compare with the values which are present in a continuous fashion in the digital elevation model. So even if I am having the ground control points or some independently collected elevation values, and then only for those points I am having comparison, otherwise for remaining areas I do not have any comparison in this one. So these points becomes very important, especially the terrain which is highly rugged. Accuracy term is also there, is a measure of that measure that aggregates or summarizes the errors within a data set. So how much error it is being carried. Suppose in case of digital elevation model, a elevation supposed to be say 100 meter, it is coming say in your digital elevation model it is coming 110 meter. Now so that means 10 meter plus value is coming, or there might be a case where supposed to be 100 meter but it is coming 90 meter. So we can say that plus minus 10 meter. So this information must be available before we employ that DM and drive certain derivatives or outputs from that. Generally DM quality is reported in a root mean square or RMSE value by the developers of those DEMs, or if you are using interpolation techniques, say kriging, at that time also you can record the errors, and the variation in error is not communicated by the single RMSE value. Now this RMSE is based on the differences between DM elevation and the elevation of the test points or ground control points measured by field survey from an existing source map and other methods. Now when you go for a very accurate assessment, then one question can also be raised that how accurate these test points are, because after all you would be using certain instrument. Say for example, you are using GPS or differential GPS technique. Now differential GPS techniques will also have their own errors. So your test data, or which you are considering as a standard data, is also suffering from some errors. So these things have to be kept in mind about these products which we are going to use in our GIS analysis. Now there are various ways: statistics, visual examination of the surface model, and statistic summarizing key morphometric characteristics of the DM can provide valuable additional information about the quality of DM. And so it is hypothesized that the distribution and the scale of errors within a DM are at least partly related to morphometric characteristics of the terrain. Because if it is a elevation model representing the elevation or terrain conditions, then we are in some time we are going to use for morphometric analysis. So if we can perform before that, then we can also use this tool to assess the errors in our input digital elevation model. An accuracy surface would give a better representation of the distribution of errors within a DM than a single RMSE value. So this, if this can be derived, then this surface, and you can know exactly in which part of your input DM it is having more errors than compared to other errors, rather than just having a single value through this root mean square estimation. Now sources of DM, which we have already discussed initially, but I am just going quickly through this one. Now if ready-made DMs are there, then how you can check that if ready-made DMs are you are using in GIS, then if you are having some test points available through your topo sheets, you can compare those test points with the digital elevation corresponding cell values of your digital elevation model and find out a standard deviation and other things, and then you can assess that which is closest, and that you can say that this is more true representation of the terrain, but it is only against certain points. Or these test points or control points can also come through GPS. There are libraries of GPS ground control points are available, which can also be employed to assess the quality of DM, how accurately it is representing a particular part of the earth. If it is self-made, that means using interpolation techniques, then I can suggest a very quick and quite accurate method of assessing which digital elevation model or which interpolation technique is suitable to you. Say for example, if you are having 100 points, elevation points available to you, which are say distributed in an area. Now before going for interpolation, what you do that you select randomly 10% of the points. These random selectors are also available with the standard GIS softwares, and you remove from original data sets. So now say here we had the 100% data, now we are having here before interpolation we are having now 90% of the data. Randomly 10% data has been selected and removed temporarily from the original data set, and do then interpolations employing 3-4 and different interpolation techniques. So you will have different surfaces here, 1, 2, 3, 4 surfaces. Then use those 10% which you kept separately. Those points you use and compare with your different DMs which you have generated. So for example, I am having one DM which has been generated. Now those 10% points I will use as test point or control points, compare the corresponding cell values, and whichever will give the closest values, I will consider that that is the best digital elevation model is suitable for my input data set. Now at this stage I am having an input of only 90% points. So what I have to do, that now I know that, say for example I reach to a conclusion that IDW is most suitable for my data set. So then I will go back to 100% points and then create a surface using IDW method, because I know that IDW is giving the best results when I compared with 10% points, and those 10% points you have selected randomly. So there is no biasness, and this way I can assess that which DM or which interpolation technique is suitable for my set of input points. And this is what it is mentioned here, that if you are going for self-made digital elevation models, then before using all points for interpolation, remove some random points, say 10% from the source data. Then use these 10% data to check the accuracy of a DM, of different DMs which you have derived from using different interpolation techniques. And once you are sure that which one is giving the closest value, use then 100%, use that particular tool or interpolation technique and create a final surface. So which interpolation technique for DM generations, as I have answered, that this answer will come from the above error check. When we will go for this kind of exercise, first 100%, 10% randomly selected, then 90%, various DMs using various techniques, and then comparing, finding the best one. And once I have identified the best one, I will use 100% points and create. So this will remove my sort of uncertainty about which method is suitable for that particular set of points. Now this exercise has to be done with each new set of the point, because we do not know what it is representing. You may end up with the same result, but it has to be done with each set of new points. So this will really help us to find out the which interpolation technique is suitable for us. So this way you can have knowledge of the errors in your data, in your input data, in your digital elevation model, and also you can, when you yourself are preparing, then you can find out the best interpolation techniques by doing a sort of exercise and then finally preparing a digital elevation model. As also mentioned in previous lectures, that the user of GIS or the data which is coming into your GIS, he must be aware about the inherent errors which are already inside the data. Because if you are aware, you will be using that data set very carefully, because when you drive a output using that data set, that output may not be that reliable which you are intending, and then whole exercise may go in waste. So it is always to have knowledge of errors and keep errors at the minimum. This is very, very important component in GIS. Thank you very much.